Hello, my name is Dr. Erin Gomez, and this is a brief overview of magnetic resonance and a basic MRI spin echo sequence. Let's talk about protons. We have protons in the fat, muscle, and sugars within our body, and of course, within water. Remember that a significant portion of our bodies consists of water, and that a hydrogen atom is just a proton, one positron and one electron, with a positive and a negative pole. Because of this, each of these protons is capable of acting like a bar magnet. Usually, the orientation of these protons is random, but they can be influenced by an external magnetic field. At the most basic level, an MRI scanner is a giant magnet and generates its own magnetic field, which we can call B0. When protons are placed within this magnetic field, they'll line up parallel or anti-parallel to the primary magnetic field, with a small majority aligning with the direction of the primary magnetic field, just going with the flow. This generates what is referred to as the net magnetization vector. We can imagine this net magnetization along the z-axis, the long axis or length, of the patient's body. In addition to aligning with the magnetic field produced by the MRI scanner, the protons in your body are also spinning along their axes like little tops or globes. This is called precession, or nuclear spin. The speed or frequency of this axial spin depends on the strength of the applied magnetic field and can be expressed by the Larmor equation. Simply put, this equation states that the precession frequency of a particle is equal to the strength of the magnetic field applied and the gyromagnetic ratio, which is a constant that is unique to each specific nucleus or element. With the protons aligned with the main magnetic field, we can influence them using externally applied radiofrequency or RF pulses. When this happens, the protons are knocked down into an alternate plane and also precess together in phase. The angle depends on the strength and duration of the RF pulse. Knocking the protons down into another plane is a change in their longitudinal magnetization. Normally, the majority of protons are going with the flow and following the direction of the external magnetic field. But with a little extra energy, which we can call excitation, protons have the ability to go against the current and instead orient themselves in the opposite direction, against that of the magnetic field. This is called anti-parallel. That's not all that happens. With some energy applied in the form of the RF pulse, the protons will also precess together in phase. We can think of this brief synchronization as the transverse magnetization of the protons. To recap, we've put some energy into the system and temporarily convinced each of these protons to sit down and get it together. This doesn't last long, much as if you were knocked off of your feet or if I yelled at my wild little children as they ran haphazardly around their playroom. Recovery is imminent. They'll behave for a short time, but they'll soon return my energy back to me as the baseline state of disorder is restored. Much like my children, the protons will recover, or return to their original state of orientation with the magnetic field and asynchronous precession. Now that we've gone over what can happen when we administer an RF pulse, let's talk specifically about what happens during a typical spin echo sequence. Remember, the flip angle induced by an RF pulse depends on the strength and duration of the pulse. The thing being flipped is the net magnetization vector. At the beginning of a standard spin echo sequence, we apply a 90-degree pulse. This means that after the RF pulse has been applied, the net magnetization vector is perpendicular to its original orientation. This orientation is achieved by eliminating longitudinal magnetization and generating a transverse magnetization vector by synchronizing proton precession. During recovery, longitudinal magnetization increases and transverse magnetization decreases. The protons dephase. This looks like a spiraling of the net magnetic vector along the z-axis. This spiraling of the net magnetization vector induces an electrical signal by a process called free induction decay, which is really just a throwback to the high school physics principle of inducing a current by rotating a magnetic field. Search the depths of your mind for the right-hand rule. A few additional terms to note. The recovery of the longitudinal magnetization of a proton occurs exponentially. The point at which 63% of the longitudinal magnetization has been recovered is called the T1 time. The time at which 63% of the transverse magnetization has been lost is called the T2 time. The T1 and T2 time is unique to each tissue type imaged. Think about a class of children running a foot race. Each will recover to their baseline heart rate at a slightly different time depending on their physical fitness. We can take advantage of these unique tissue properties and alter the MRI sequences to highlight them. This is called weighting, and discussion of this is for another time. That wasn't so bad, was it? Seemed too good to be true? In a way, it is. There are a few caveats and drawbacks to the concept of free induction decay. Number 1, it only applies to 90-degree pulses. Number 2, the signal decays very rapidly and requires a very fast scanner to detect. Number 3, the dephasing of protons occurs at a speed known as the T2 star constant. This exponential decay in the synchronization of proton spins is due to the fact that each proton experiences the magnetic field at a slightly different strength, meaning there is never true uniformity in precession. These differences in precession end up compiling, leading to increasingly asynchronous spins. Because each proton already experiences the magnetic field differently than its neighbors, any inhomogeneity in the magnetic field makes dephasing, and thus signal dropout, even worse. These are called T2 star effects. On MR imaging, these T2 star effects can appear as diffuse loss of signal, or black holes, in areas where the magnetic field is particularly distorted. Because these effects are due to an inhomogeneous magnetic field, we can liken them to distractions in a child's environment. T2 star effects seem terrible. Isn't there any way to fight them? Fret not. The answer is yes. The good news is that we can combat T2 star effects and their resulting signal decay with the addition of another RF pulse. To understand this, we must remember that although magnetic field inhomogeneity is inconvenient, it is manageable in the sense that the differences in precession speed that they cause are fixed and predictable. As some protons lag behind their faster counterparts, we can apply a 180-degree refocusing RF pulse that instructs all of the protons to turn around and precess in the opposite direction. Much like the classic tale of the tortoise and the hare, though the tortoise is far behind the rabbit, if we ask both to turn around and head back to the starting line of the race, they'll catch up to each other and arrive at the same time due to the differences in their speeds. The crowd goes wild. It's a tie! When the proton precession syncs up following the 180-degree pulse, more energy is released back into the system. This is called an echo, and it is the information collected by the MR scanner which will eventually generate a medical image. We can liken the 180-degree refocusing pulse and the synchronous precession it creates to an elementary school class photo shoot. The teacher may need to raise her voice in order to get the class to focus its attention on the photographer and achieve a yearbook-worthy shot, the echo. We can apply additional 180-degree pulses to achieve multiple echoes, photo after photo after photo, to continue decreasing the T2 star effects. Eventually, however, the students have nothing left to give. Less and less energy is yielded back with each echo. Eventually, dephasing occurs completely and the echo dies out. Once that happens, the sequence must be restarted again with another 90-degree pulse. Imaging in this manner is called spin echo or fast spin echo imaging. We can use universal diagrams to depict what happens with specific MR sequences. Let's use one to recap the basic fast spin echo sequence that we've just discussed. Protons are aligned with the main magnetic field, B0, and are precessing randomly. A 90-degree RF pulse is applied, eliminating longitudinal magnetization and producing a transverse magnetization vector as protons precess in phase. Longitudinal recovery and transverse decay occur, producing a signal by a free induction decay, which is susceptible to T2 star effects. A 180-degree refocusing pulse temporarily rephases proton precession, producing an echo which can be read out by the MR scanner. The moment that the echo is produced is called the TE, or time to echo. We can apply multiple refocusing pulses in an attempt to capture as many echoes as possible. The echoes become successively weaker until the signal dies out completely and the sequence must be restarted. The time between repetition of sequences is called the TR, or time to repetition. That's all for now. This concludes our overview of magnetic resonance and the basic MRI spin echo sequence.